Resonance between parallel RL and RC circuit. So here it is a parallel circuit, but it is RL is in one branch and RC is in one branch. They are in parallel. So RL circuit and RC circuit are connected in parallel, and that combination is connected to a voltage source. Now there is a current coming from the voltage source, and that current divides into the branches. I1 is the current in RL branch, and I2 is the current in RC branch. So here we are taking R1 is not equal to R2. So R1 is different from R2. So writing KCL at the node. So if you write KCL at the node, we get I equal to I1 plus I2. I is equals to I1 plus I2. So here reactance offered by the inductor is JXL, let it be JXL, and reactance offered by the capacitor is minus JXC. So at that time, what is the relation between V impedance and I1? V equal to R1 plus JXL into I1, and I1 equal to V by R1 plus JXL. And similarly, V, I2 and impedance relation is V equal to I2 into R2 minus J XC. So I2 equal to V by R2 minus J XC. So I1 is equals to V by R1 plus J XL, and I2 equal to V by R2 minus J XC. So we get, if you substitute in equation 1, so we get I is equals to V upon R1 plus J XL plus V by R2 minus J XC. So taking V as common and taking that V to left hand side of the equation, we get a current to voltage ratio, which is admittance. So admittance is equals to, so current by V, which is equals to 1 by R1 plus J XL plus 1 by R2 minus J XC. And eliminating, so to separate real terms and imaginary terms, we are rationalizing this term and we are rationalizing this term. So altogether we get y is equals to R1 minus JXL by R1 square plus XL square, and here plus R2 plus JXC by R2 square plus XC square. So if you write all real terms at one place and imaginary terms at one place, y is equals to, which is in G minus JB form. So R1 by R1 square plus XL square plus R2 by R2 square plus XC square minus J XL by R1 square plus XL square minus XC by R2 square plus XC square. So which is in the form of y equal to Z minus JB. So where G is called as conductance. So after comparing this with this equation, so G is equals to R1 by R1 square plus XL square plus R2 by R2 square plus XC square. Unit is mho. So similarly, this part is a susceptance part, which is B. B is called as susceptance. So susceptance B is equals to XL by R1 square plus XL square minus XC by R2 square plus XC square mho. So here the circuit will be at resonance. So finally this RL circuit and RC circuit is at resonance. So resonance means imaginary part should be 0, reactance part should be 0. Here it is susceptance part is 0. In admittance susceptance, we are equating susceptance to 0. Susceptance becomes 0 at resonance. So we are equating that susceptance to 0. The circuit will be at resonance when the imaginary parts of capacitive and inductive admittances are cancelled. That is XL by. So when this is 0, so this term is 0. So at that time XL by R1 square plus XL square, which is equal to XC by R2 square plus XC square. So now we are replacing XL with omega L and XC with 1 by omega C. So omega L by R1 square plus omega square L square, which is equal to 1 by omega RC by R2 square plus 1 by omega R square C square. So for omega we are taking omega R, because so this is the condition for resonance. So if we simplify, we get omega R L by R1 square plus omega R square L square, which is equals to 1 by R2 square omega RC plus 1 by omega RC. So if we go on simplifying this again, so we get this term So after this we get R1 square plus omega R square L square, which is equals to L by C 1 by R2 square omega R square C square. So if you take this L by C into the brackets, we get L by C plus R2 square omega R square LC. So after that, so getting this term R2 square omega R square LC square to left hand side of the equation and R1 square to right hand side of the equation, and taking omega R square as common, we get omega R square L square minus R square LC, which is equals to L by C minus R1 square. So again taking L by LC as common from these two terms, we get this expression. So finally extracting omega R square is equals to 1 by LC into L by C minus R1 square by L by C minus R2 square. So resonant frequency, so this is in radians per second, moreover it is a square, and if you want this in hertz, so here resonant frequency in hertz is equals to 1 by 2 pi 1 by root LC into and square root of this, that is L by C minus R1 square by L by C minus R2 square whole power 1 by 2 hertz. So if you want this in radians per second, take this 2 pi to left hand side of the equation, at that time you get omega R, resonant frequency in radian per second. So that is 1 by root LC into root over 1 by root over LC L by C minus R1 square by L by C minus R2 square. So or otherwise 1 by root LC L by C minus R1 square by L by C minus R2 square whole power 1 by 2. So if R1 equal to R2, so what happens if R1 equal to R2? At that time this becomes 1. So at that time FR equal to 1 by 2 pi root LC. So if resistances are equal, here we are taking different resistances. R1 is not equal to R2, that is the expression. Even if R1 equal to R2, which is equal to R, so at that time we get resonant frequency as 1 by 2 pi root LC. So this is all about RL and RC circuit. RL branch and RC circuit are connected in parallel and resonance to RL and RC circuit. So resonance between parallel RL and RC circuit.